So, talking about sound waves today. All right. Hmm. Don't die. Okay. What I have here, I have a bell suspended in a jar. Okay. Now, what I'm going to do is I'm going to take this vacuum pump and I'm going to suck the air out. It's a little finicky. Okay. Okay. You can kind of still hear it a little bit, but listen as I let the air back in. Okay. You get to that? So, does sound require a medium? Yes. There has to be something. Now, the reason why you could hear it after I sucked the air out is because the the vibrations were going to the glass themselves, and so you could. It was still like I could feel as I was holding it. I could feel it vibrate. Um, but a large part of that was reduced because of all the air taken out of it. Okay. Now, okay, so you have to have a medium for air, sorry, for sound to travel. So it can travel through water, like liquid, it can travel through a solid, travel through a lot of things, but needs something. Okay. Um, so like in space, okay, no one can hear you scream. Have you ever heard that? Like that horror, like so, like it really do a number on Star Wars, like the audio file, like kind of like that's a bummer. So do that. Yeah, all those sounds gone. All right, so oh yeah, there's a bell in there. Yeah. All right, so um, the source of all things, all sound is something vibrating. Okay, so ooh, this is a tuning fork. It's a tuning fork. Um, this is vibrating at a certain frequency. Okay,
It sounds like when you listen to a show and you hear the ocean.
No, it is. You
know?
Yeah.
Oh.
Maybe you accidentally
It's interesting. I don't know what I was expecting. That was I expected anything like aliens.
Yeah.
That's right. And so yeah. Where's the demo? Oh, oh, I don't like that. Oh, that's cool.
Yeah.
Okay.
Okay. All right. So this is. Oh, I need to show you this. Okay. So this is to prove to you this is vibrating. That was weak. That was better.
That's entertaining. There's just holes in it. It wasn't like.
Ready?
Oh.
So after it hits the water, does it stop vibrating?
Yeah, it's a dead, like it's, yeah. Oh.
There's two things.
Okay. So the process by which you hear something. So that tuning fork is vibrating back and forth, pushing on air molecules that create pressure waves, longitudinal waves. Okay, so you have high pressure here, low pressure, high pressure, low pressure, high pressure, low pressure. Okay, and that pressure wave is going out in a sphere at 343 meters a second. Like if you throw a rock in a pond, the waves go out in a circle. It goes out in a sphere in all directions. Okay, 343 meters a second. Okay, when those pressure waves hit your eardrum is kind of like, you know how your mom is like, don't put a trash bag over your head, like you'll die, like you'll suffocate. Like at some point you did, like you put, like I put, you put your sandwich baggie over your mouth, and then did that, right? Like, okay, and the sandwich baggie was like like it'd be sucked in, blow it out, Sucked in, blow out. Okay, that's exactly what your eardrum does when it experiences high pressure. It's pushed into your head, and then when it experiences low pressure, it's sucked out of your head. And so this happens fast enough, and that's converted to electrical signal, which we perceive as sound. Okay, cool with that. So here's a quick trip down the ear canal. Okay, so we're gonna do like magic school bus. The music on this is kicking. A little bit of polka. It always sets the mood. So we're going down the ear canal. That's your eardrum. Okay. So if you ever break your eardrum, that's the part that ruptures, that thin film, that membrane. Okay. And these are the smallest bones in your body, the eardrum bones. These are vibrating in response to this vibrating. Okay. So now we're behind the eardrum, like we're inside your head. Okay, so these bones are vibrating, and it gets to this point here, and this acts like a plunger on a toilet, like, and it's acting like high pressure, low pressure for fluids. And then this thing is what converts that high pressure, low pressure, and fluid pressure to electrical signals. And then that message, those signals are sent to your brain, and you perceive that as sound. Okay. If you've ever been dizzy, this is the thing that's been messed with. Okay. Or vertigo. This is the fluid in your ear that helps with equilibrium and balance and all that stuff. This is the thing that's getting messed up. Okay. Cool. It's a little tour through the ear, the inner ear. Okay. Now, here come the lights. In my opinion, well, it's not my opinion, this is a fact. There's so many different things that have to go right for us to hear. Like, the process of hearing is super involved. It's pretty amazing to me that most all of us can hear. Like, that's just a lot of things working well together, like working correctly. It's just cool. Now, so this tuning fork is designed specifically to vibrate at 341 hertz. This goes back and forth 341 times every 1 Mississippi. Okay? It's pushing on air molecules, and those pressure waves are going and making your eardrum vibrate at 341 cycles per second. And we take that vibration and we hear noise from that. We hear sound of this. Like not the high pitch, but the there. That one. Okay? Does that make sense? The range of human hearing. So this was 341 hertz. That's not that high of a noise. It ranges from 20 hertz to 20,000 hertz. Okay, so the higher the frequency, the higher the pitch. Okay, you can feel that if you hold on to your throat, your vocal box, your vocal cords, and oh, like this versus like this. You can feel it really like a low frequency, high frequency. Okay, you should try it. You can do it by yourself in the bathroom or something sometime, but like it's okay. For those who have some kind of like musical understanding of some sort, okay, the music scale is divided up into octaves. Okay, och, 8, octopus, octagon, octave, have 8 notes. Okay, every octave you have the same note, so it's like the do, re, mi, fa, sol, la, ti, do, do, do. Same note. Hey, ooh, I have not looked. You can look. So does everybody go with that? Like the octave thing? Okay. So every time you go up an octave, you double the frequency. So I think this is right. 256 hertz is middle C. Okay, so if you play piano, that's like your starting point. The octave above that is 512 hertz. The octave above that is 1024. So in between those, there's 8 notes. In between those, you subdivide that eight times, like into 8 steps. Okay, so it's not a linear scale, but I'm not going to necessarily quiz you on those frequencies, just so you have some kind of idea of how that works. Okay, the louder something is, the greater the amplitude, the more air molecules are being moved. Higher the pressure, lower pressure, high pressure, low pressure. Okay, go to that. All right. Bum, 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 bum. Okay, so we have carpet in our hallways, so this demo doesn't work out so hot. But Rachel, could I implore your help, please? Hang on to that. Squat on the floor, please. Oh, we need a demo of this.
Oh, I used to do it. It's not good. When did they do it? Oh, 7th grade or 6th grade.
Actually, you know what would be better?
Oh, what's her name? George.
All right. So, Rachel, which way is easiest? Yeah, you can sit down if you want. Which way is easiest to go, like this way or this way for you? It doesn't matter. Okay. All right. So what we're going to do is we're both going to go the same way. We're going to do a wave pulse. What I want you to observe is what does it look like when the two waves overlap each other. Okay. So Rachel, what it's going to look like is just a quick, something like that. Okay. So 3, 2, 1, go. 3, 2, 1, go. 3, 2, 1, go. Okay. 3, and I'm going to do it. You still go on go. Okay. 3, 2, 1, go. 3, 2, 1, go. 3, 2, 1, go. 3, 2, 1, go. Okay. What happened when they overlapped each other? Got bigger. I'm going to try it again. Ready to watch for it now that you know the answer. 3, 2, 1, go. Anybody see that? Okay. That's known as constructive interference. Okay. We're going to go destructive interference. This one's a little harder to see. Okay. Rachel, do the same thing. 3, 2, 1, go. 3, 2, 1, go. 3, 2, 1, go. You know what? You guys probably have a harder angle. See if, let's try this. Thank you, Rachel. Caroline, you're going to do the same thing Rachel just did.
It's going right.
Okay, we're going right here. I think.
Screw the desk.
Okay, here's where you need to be looking. You need to look like down along this thing. Like not across, but like get over there or get over here and look down. I think it'll be easier to see.
No, he says you want to like stand over here. Yeah, but like I still feel like I'm in the middle of it, you know.
Okay. Which way you go? Okay, so 3, 2, 1, go. Go a little more like abrupt. 3, 2, 1, go. You see that better? Is that better or worse? Sorry. 3, 2, 1, go. Okay. Now, one thing I want you to observe. This one's harder to see. This is destructive interference. I'll show you a slow motion video of this here in a second. But what I want you to look at is, do the waves bounce off of each other or do they pass through each other? Okay. I'm going this way. Caroline's going this way. Caroline's going this way. Okay. 3, 2, 1, go. 3, 2, 1, go. 3, 2, 1, go. Do the waves bounce off each other or pass through each other? All right, here we go. 3, 2, 1, go.
Oh yeah.
3, 2, 1, go. Bouncing means they like mine goes and hits yours and comes back to me. Passing through means, okay, 3, 2, 1, go.
Yeah, no, it goes all the way down. They're passing through.
Okay, mine goes this way. Caroline's goes this way. 3, 2, 1, go. See what gets to me. See what gets to her. 3, 2, 1, go. They pass through. They pass through. Ready? 3, 2, 1, go. This. Here we go. 3, 2, 1, go. Look at that. Get to that? We could, but thank you.
Oh shoot, I need to put my mom right now.
It's a watch. It's not a warning. It's a watch. Listen. We've been in a tornado watch since like beginning of this week. Like they've seen. No, I think. Okay. Okay. No, they're looking for it. Yeah, okay. Yeah, we're going, yeah. All of us in the science wing. Okay, so here's constructive interference in slow motion. Okay. Okay, here we go. Ready? Now, here comes. I'm going to pause it. Okay. To figure out to figure this out, what we're doing at this, let's just look at a certain moment in time right here. At this moment in time, this has an amplitude of +2. This one at this same moment in time has an amplitude also of +2. So when these two waves overlap, you're just adding their amplitudes. So you get +2, +2. So you get 4. Folks, there are way too many side conversations going on. Okay, so you get a total amplitude of 4. You good with that? Okay, constructive interference. Now, this doesn't have to be, so here, this has an amplitude of like 1.3, making that up, or estimating that. At that same moment in time, this has an amplitude of 1.6. Adding those together, you get 1.3, 1.6, you get 2.9. Does that make sense? Okay. Constructive interference. Okay. So you can do that at any moment in time. So doing that same trick. Okay. Now, destructive interference. Notice they pass through each other. Okay. Oh. Oh. Well, that'll work. Okay. So at this moment in time, we have an amplitude of roughly 2. At this moment in time, same moment in time, we have an amplitude of -2. So we add those together, +2 plus -2 gives us 0. All right, so at that moment in time, it's completely destructive. Okay? Now, another moment in time right here, we've got +2, and we have that same moment in time, we have -1. Adding those together, you get +1 as the resultant wave pattern. That's still destructive interference because they're going against each other. Jacob? No, they will not bounce. If there's ever a point where you're changing the medium like it goes, let's see, what's a good example of that? If I had um, a super dense slinky or like a hose, and I did that when the slinky from the wave from the slinky, when it hits the hose, some of that will go make the hose move, but some of it will bounce back towards me. So if it's a fixed impost, like a boundary, then it bounces. Okay, but through the medium, no, it doesn't bounce. It'll pass through. Okay, good with that. So if you have two waves going on, wave patterns, like here we have the solid black and the dashed black. When they overlap each other, they interfere. At some points are experiencing constructive interference, other points are experiencing destructive interference. Okay, so here I'm making these numbers up. Let's say we've got 2, or like 3, and 3 gives us 6. Here we have like 4, and -4 gives us 0. That's destructive, obviously. Here we have 0 and 3, so the total amplitude is 3 at that location. Here, this is still considered constructive interference because they're working with each other. They're adding them up. So like -3 plus -3 gives you -6. Good with that? And so you end up with this resulting wave formation. Okay, a lot of trig identities right there. Pretty cow folk. Okay. All right. Okay. So what this is giving you an example of is like a wave pulse has an amplitude of +2 going this way, and this one has a -1. When these overlap, what's the resultant wave formation? What does that look like? Tell your neighbor. Okay. Here's what this is doing. Okay. Here's what this is doing. This is -1. Overlapping that, you get +2 plus -1 gives you a resultant wave of +1. So B. See how that's working? Okay. That was a simple example. This next one's a little more involved. You've got this wave pulse and this wave pulse. You have +4, -4, +2. When this overlaps this completely, what is the resultant wave pattern? Tell your neighbor. Correct answer is okay. Here's +2. So you get +2 plus +4 gives you +6. That makes sense? And then here you get +2 plus a -4. So you get -2. Correct answer is A. JP. Correct. Yep. Okay. So, and just to jump on that, like that's why wireless everything works. Like there's tons of wireless signals going through. They're all waves, but yet we can still, they don't, like they still pass through each other. So examples of where you might see interference in life. Ben. No, they're not sound waves. They're electromagnetic waves, and which we'll talk about next chapter.
Like, why can you hear certain waves?
Because, like, speaking specifically towards signals, they aren't pressure waves. They're electric and magnetic fields that your eardrum. Now, if they're pressure waves, you can have. We have a certain range of hearing. If it's too low, it's like it doesn't register as sound to us, and if it's too high, it's vibrating too fast for the anvil and the bones in our ear to vibrate. Can't vibrate that quick.
So how do, like, what waves are sent, like, from my phone to my wireless earbuds?
So the easy answer is Bluetooth, but we'll talk about what that is.
And how does it work through a wall?
That's another great question. Can I put that on? I shouldn't. I have that thought. I shouldn't. That's coming into the chapter. It's coming. We'll have a whole conversation. It's a great conversation. Okay. Here we go. So, examples of other examples of interference in life. So if you've ever been boating, and you're like tubing or water skiing or whatever, and you fall off, the boat has to come around and pick you up, so it does a circle around you, and that's where you get these ginormous waves. That's because the wakes are interfering with each other. If you've ever been like jet skiing or wave running, you always want to hit jumps, but let's say there's no boats around to make big waves. What you do is you go in a big circle and you try to time it for the wake to come together, and like sometimes like you nail it and it's awesome. Other times it's like I thought I made waves. You did. Sometimes they're constructive interference and are huge. Other times they're destructive interference and it's like riding through still water. At that moment in time, you turn around and you still see waves, but why didn't you? It's just at that moment they were destructively interfering with each other. Does that make sense? Okay. Other examples. Um, all right. So back in the day, these were my earbuds. This is how we did it back then. It was like boom, well, boom boxes. That's the correct terminology for these things. Okay. So what I'm going to do is I'm going to hook up a speaker. I'm going to hook up a speaker to okay. Okay. Now, if I hook up a second speaker, 1, 2 speakers, 1 speaker, 2 speakers. Now, That's not surprising. We expect it to get louder. What I'm going to do is I'm going to flip the wires. Oh, come on. One speaker, two speakers. One speaker, two speakers. Flip the wires back. 1, 2. 1, 2. Flipping them. 1, 2. Okay. Now, to understand what's going on here, we've got to remember how speakers work electromagnetically. Okay? So, the current goes one way, forces the cone out. The current goes the other way, it forces the cone back in. Does that make sense? Okay? Now, and this vibrates and creates its own sound wave. The vibrations of the cone. It's pushing air molecules. Okay? If we hook up the other one correctly, they're both experiencing the same signal. And so you get constructive interference. But if you hook them up what's called out of phase incorrectly, when the current's going one way in one wire, the current's going the opposite way in the other wire. And so here where you get compression, you get rarefaction here. So this is causing destructive interference. So two speakers can actually be quieter than one speaker because they're just like destructively interfering with each other.
Can you get like constructive negatively?
Yeah. Yeah, it's still constructive interference. So what I think when you mean by that is like you have two things going down.
Yeah.
So it's the vibrations between high pressure, low pressure. If you just had high pressure, that's not loud. That's just high pressure.
Yeah.
But it's the high pressure, vibration, oscillation, that's what creates sound waves. Does that make sense?
Yeah.
So a loud noise would be high and then low, like a big high, big low. Big high, big low, big high. That would be loud. Okay. Noise canceling headphones uses this same technology or this science behind it. So noise canceling headphones have a microphone in the headphones and it records the outside noise. And then it plays back the outside noise just with the opposite current. So it still plays that sound, but it destructively interferes the sound waves that are coming in from the outside. But in addition to that, it also plays your music. Does that make sense? And so, pretty cool. All right. All right. Another application of interference. What I have here are two tuning forks. Okay. And they have the same note. Okay. Now, what I'm going to do is I'm going to add some weight to one side. And what that's going to do is going to make it harder to vibrate because there's more mass. So when it's lighter, it's like, yeah, you add more mass, it's like, oh. So this is going to make this lower. It's going to make it flat from a music standpoint. Okay. Listen what happens when these two notes are played. You hear that? That in physics terminology is known as a beat. Okay? A beat, the wom 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 wom. Okay? You'll need to know this for your homework. Don't pack up. The beat frequency is the difference in the frequencies between the two between the two notes being played. Okay? And here's what happens. Here's what causes this. You got two sounds being played. Oh my. Thank you. You got two sounds being played. Thank you. And at some point, they're in phase with each other. And so you get constructive interference. At other points, they are out of phase and you get destructive interference. So you get the wong, 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 wong effect. Does that make sense? Okay. How frequently the wong, 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 wong happens is determined by that equation. Okay. So as I get closer to the same note, what's going to happen to the beat frequency? As you get closer to the same note, it doesn't happen as frequently. And you can actually tune flutes and piccolos relative to each other with this idea. Okay, it works well with higher pitched instruments because we're more perceptive to that. Okay, so as you get closer to the same note, happens less frequent. Okay, good with that. An analogy to this isn't really beats, but you can relate to it. If you ever pulled up behind someone at like in a left-hand turn signal, and your turn signal is going, and then you see somebody else in front of you, and it's like, yeah, it's like, hey, look, yeah, we're jiving. Oh, man, that's out of phase. And then all of a sudden it's like, boom, 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 yeah, we're in phase, yeah. Okay, good with that. Worksheet due tomorrow.